Section 29 of the Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The Science, History of the Universe, Volume 1, edited by Francis Rolt-Wheeler, Astronomy. Chapter 20, Comets, Meteors, and Meteorites, Part 2. Biela's comet, discovered by an Austrian officer of that name at Josephstadt in Bohemia, February 27, 1826, presents as interesting features as that of Encke. It was seen 10 days later at Marseilles by the French astronomer Gambart. Both observers announced its discovery and the computation of its orbit in the same issue of the Astronomische Nachrichten. Though the comet was identified with similar appearance in 1772 and 1805, it was not visible after the latter date with the naked eye. In 1832 Sir John Herschel observed it as a conspicuous nebula without a tail. While the day of active superstition in regard to the appearance of comets has passed with the demonstration of Halley's theory, nevertheless Biela's comet occasioned widespread popular excitement, founded moreover on the statements of scientific men that a collision with the Earth might occur. The possibility is one of the remotest of cosmical happenings. In 1846 Biela's comet reappeared, and when first seen, November 28th, presented no unusual appearance. Gradually it became distorted, however, and elongated. Within 2 months it divided into 2 separate bodies, which were visible until April 16th of the following year. This striking phenomenon of a double comet was noted by many astronomers at different observatories, and thus established what Seneca had reproved Ephorus for supposing to have taken place in 373 B.C., and what Kepler had noted in 1618, but without convincing astronomers at large of the correctness of his impression. These 2 Biela comets contained a small amount of matter and performed the revolution around the Sun independently without experiencing any appreciable mutual disturbance, which indicated that at an interval of only 157,250 miles their attractive power was virtually inoperative. Various interesting phenomena showing internal agitation were observed, and variations of brilliancy and form were distinctly evident. In 1852 Biela's comet again reappeared in its double form, but since that time has not been observed. The disruption occasioned by its proximity to Jupiter in 1841 is believed to have been the beginning of the disintegrating process which resulted in its disappearance. The greatest comet of the 19th century was that of Donati, which was seen by him at Florence, June 2, 1858. By the end of September, when the comet had reached its perihelion, the tail had attained full development, and on October 10th it stretched in a maximum curve over more than a third of the visible hemisphere, representing a length of 54,000,000 miles. For the 112 days during which it was visible to the naked eye, the fullest observations were made. The comet stands by itself, as it is not possible to identify it with any other. At aphelion its orbit extended out into space 5½ times the distance from the Sun to Neptune, and for its circuit, which is effected in a retrograde direction, requires more than 2,000 years, so that its next return should be about the year 4000 A.D. It was computed by M. Faye that the volume of this comet was about 500 times that of the Sun. On the other hand, he calculated that the quantity of matter it contained was only a fraction of the Earth's mass. This shows how almost inconceivably tenuous the material forming the comet must have been, much more rarefied indeed than the most perfect vacuum which can be produced in an air pump. This tenuity is shown by the fact that stars were seen through the tail as if the tail did not exist. A mist of a few hundred yards in thickness is sufficient to hide the stars from our view, while a thickness of thousands of miles of cometary matter does not suffice even to dim their brilliancy. Dr. Barnard states that our knowledge of the extremely rapid transformations in the tails of comets dates from the photographs of Swift's comet of 1892, taken at the Lick Observatory, and similar ones taken of the same object by Professor Pickerington at Arequipa. While only an insignificant affair visually, but fairly visible to the naked eye, Swift's comet showed upon the photographic plates the most extraordinary and rapid transformations. One day its tail would be separated into at least a dozen individual streams, and the next present only 2 broad streamers, which a day later had again separated into numerous strands, with a great mass, apparently a secondary comet, appearing some distance back of the head in the main tail, with a system of tails of its own. The photographs of Brooks' comet of 1893 show such an extraordinary condition of change and distortion in the tail as to suggest some outside influence, such as the probable collision of the tail with a resisting medium, possibly a stream of meteors. The long series of photographs obtained of this comet show great masses of cometary matter drifting away into space, probably to become meteor swarms. Had it not been for photography, the comet, instead of proving to be one of the most remarkable on record, would have passed without special notice. Though these phenomena were so conspicuously shown, scarcely any trace of the disturbance was visible with the telescope. On account of the apparent insignificance of the comet visually, no photographs were made of it elsewhere during its active period. The application of photography to cometary studies has been an important feature of the investigation of later comets, none of which since 1882 have been marked by great brilliancy. The general nature and appearance of a comet is thus clearly described by the late Professor R.A. Proctor. When first seen in a telescope, a comet usually presents a small round disk of hazy light, somewhat brighter near the center. As the comet approaches the Sun, the disk lengthens, and if the comet is to be a tailed one, traces begin to be seen of a streakiness in the comet's light. Gradually a tail is formed, which is turned away from the Sun. The tail grows brighter and longer, and the head becomes developed into a coma surrounding a distinctly marked nucleus. Presently the comet is lost to view through its near approach to the Sun, but after a while it is again seen, sometimes wonderfully changed in aspect through the effects of solar heat. Some comets are brighter and more striking after passing their point of nearest approach to the Sun, or perihelion, than before; others are quite shorn of their splendor when they reappear. On the other hand, the comet of 1861 burst upon us in its full splendor after perihelion passage. As a comet approaches the Sun, a change takes place in the appearance of the coma and nucleus, and in some instances a tail is generated. The process actually observed is generally this. In the forward part of the nucleus a turbulent action is seen to be in progress, leading to the propulsion toward the Sun of jets or streams of misty looking matter. Sometimes a regular cap or envelope is seen to be projected in this manner toward the Sun, or even a set of envelopes one within the other. The matter thus thrown off is not suffered to pass very far from the nucleus toward the Sun, but is swept away, as fast as formed, in the contrary direction. If the funnel of a steam engine were directed forward instead of upward, then the appearance presented by the emitted steam as the engine rushed on (against a hurricane, suppose, to make the illustration more perfect) would exemplify the process which seems to be taking place around the front of the nucleus and far behind it as the matter formed is continually swept away from the Sun. The same Sun which attracts the nucleus seems to repulse the emitted matter with inconceivable energy. When we see the tail of the comet, occupying a volume thousands of times greater than that of the Sun itself, the question naturally suggests itself: how does it happen that so vast a body can sweep through the solar system without deranging the motion of every planet? Conceding even an extreme tenuity to the substance composing so vast a volume, one would still expect its mass to be tremendous. For instance, if we supposed the whole mass of the tail of the comet of 1843 to consist of hydrogen gas, the lightest substance known to us, yet even then the mass of the tail would have largely exceeded that of the Sun. Every planet would have been dragged from its orbit by so vast a mass passing so near. We know, on the contrary, that no such effects were produced. The length of our year did not change by a single second, showing that our Earth had been neither hastened nor retarded in its steady motion round the Sun. Thus we are forced to admit that the actual substance of the comet was inconceivably rare. A jarful of air would probably have outweighed hundreds of cubic miles of that vast appendage which blazed across our skies to the terror of the ignorant and superstitious. The dread of the probable evils which might accrue if the Earth encountered a comet will possibly be diminished by the consideration of the extreme tenuity of these objects. But the feeling may still remain that influences other than those due to mere weight or mass might be exerted upon terrestrial races in the course of such an encounter. On account of their enormous volumes, it is not so utterly improbable that we should encounter them as that we should meet the comparatively minute nuclei. In fact, the Earth actually did pass through the tail of a comet in 1861. About the hour when it was calculated that the encounter should have taken place, a strange auroral glare was seen in the atmosphere, but beyond this no effect was perceptible. In distinction to the comets moving in regular orbits around the Sun, the possible portions of one much larger cometary body which became dispersed by gravitational action or through violent encounter with the Sun's surrounding must be mentioned. These comets, which apparently have been seized by the gravitative attraction of planets, are compelled to revolve in short ellipses around the Sun well within the limits of the solar system. These comets are spoken of as captures, and while Jupiter, Saturn, Uranus, and Neptune each possess families of this kind, it is the first named which are the most important, as they number about 30, and in this family may be included not only the bodies that Jupiter has attracted, but those that have been robbed from other planets. Comet families are not found in the case of the terrestrial planets, because of the gravitative power of the Sun in their vicinity is so much greater than any attractive force which they could manifest. In addition, when a comet enters the inner portion of the solar system, it has such velocity that the gravitational attraction of the planets within these regions is not powerful enough to cause any appreciable deflection. If a captured comet is acted upon by further disturbing causes, its new orbit may be disarranged and it may be again diverted into celestial space. The nature of these orbits is shown in Fig. 34. The facts learned from modern cometary study are summed up by Miss Clerke as follows: First, comets may be met with pursuing each other, after intervals of many years, in the same or nearly the same track, so that the identity of orbit can no longer be regarded as a sure test of individual identity. Secondly, at least the outer corona may be traversed by such bodies with perfect apparent immunity. Finally, their chemical constitution is highly complex, and they possess, in some cases at least, a metallic core resembling the meteoric masses which occasionally reach the Earth from planetary space. The first serious study of the physical nature of comets' tails was undertaken in 1811 by Dr. Heinrich Olbers, the astronomer of Bremen. He assumed that the formation of a tail was due to expelled vapors on which two forces, solar and cometary, acted and balanced each other. In other words, he believed that the tails were emanations, not appendages, and consisted of rapid outflows of highly rarefied matter, which in great part had become permanently detached from the nucleus. This theory is especially interesting in the light of modern investigation. It served for many years until that of Bredichin, who in an examination of various comets' tails found that the curvilinear shape of the outline fall into one or another of three special types, as indicated in the accompanying illustration. Type 1, or the straightest, is most probably due to the element hydrogen. In type 2, a number of hydrocarbons are present in the body of the comet, while in the third type iron or some element with high atomic weight was assumed. Some comets may have tails of more than one of these forms, as, for example, in the case of Donati's comet, which had a straight as well as a curved tail. Of type 2, comets with a number of tails have been recorded, such as the one of the year 1744. Bredichin calculated that a repulsive force adequate to produce the straight tail of type 1 need only be about 19 times as much as the attraction of gravitation, while tails of the second type a repulsive force about equal to 3.2 to 1.5 times that gravitation would suffice, while those of the third type would require a repulsive force of about 1.3 to 1 times that of gravitation. These parts are nearly inversely proportional to the atomic weights of hydrogen, hydrocarbon gas, and iron vapor, which ratio suggested to Bredichin the composition of the various types of tail. While he was unable to demonstrate that the tails were the result of electrical action, yet he assumed some hypothetical repulsive force, which electrical action seemed to explain better than any other. Professor E. Barnard, in 1905, stated that a repellent influence of some sort must come from the Sun, and with it he included an ejecting force proceeding from the comet itself and a resistant force of some kind. The repellent force from the Sun may be found in the pressure of light, which Professor J. Clerk Maxwell assumed must be exerted by light rays according to mathematical reasoning. Radiation pressure, as it is termed, was not experimentally proven for many years, but in 1900 to 1901 it was established as a scientific fact by the Russian physicist Lebedev, and in America by Nicholas and Hall. This principle thus demonstrated, Professor Svante Arrhenius applied cosmically and held responsible for the generation of streams of matter flowing from the comet's head. As the comet approaches the Sun, this pressure exceeds the force of gravity and acts upon the cometary substance so as to drive out multitudes of the minute particles in a direction away from the Sun. Such a swarm of particles receiving the light from the Sun would appear as the familiar luminous streamer recognised in the comets' tails. When examined with the spectroscope, a comet's tail shows a faint continuous spectrum, produced doubtless by the sunlight reflected by the small particles, in addition to spectral bands due to gaseous hydrocarbons and cyanogen. Cyanogen is due to electric discharges, for such discharges are observed in comets whose distance from the Sun is so great that they cannot appear luminous owing to their own high temperatures. In other words, the composition of a comet is not unlike the blue flame of a gas stove, which is a combination of hydrogen and carbon. As the comet dashes toward the Sun and its temperature consequently rises, the spectroscope reveals the presence of iron, magnesium, and other metals in the nucleus. With a closer approach to the Sun, the hydrocarbons split up into hydrogen gas and hydrocarbons of a higher boiling point. Finally, a time comes when these more refractory hydrocarbons in turn decompose into free carbon in the form of soot. Because interstellar space is airless, the soot cannot burn, but must accompany the comet in the form of a very fine dust. This dust, propelled away from the Sun by radiation pressure, constitutes the tail of many a comet. Some of the soot particles may be larger than the critical size. They will be jerked forward toward the Sun in advance of the comet to form what is known as the comet's beard, a rather rare phenomenon. This phenomenon of the pressure of light is able to explain the fact that the minute particles ejected from the nucleus of a comet can pass over great distances in small intervals of time, which was one of the hardest points to overcome in explaining the rapid change of position of the comet's tail passing around the Sun. In addition to the light pressure of the Sun, the electrical energy of the Sun must be called upon to explain the occurrence of tails which are ejected from the nucleus with a force that may be as much as 40 times more powerful than gravitation. End of section 29.